All right, so we've looked at some exponential equations and seen how we solve that by using our trick of taking a logarithm of one side equal to a logarithm of another. But what about a logarithmic equation? What if we have the logarithm in the equation in the first place, like this one right here? We've got the logarithm base 3 of x plus 1 is equal to 2. Well, if we're going to solve this kind of equation, again, we can apply some of our formulas right here. After all, our definition, if you recall it, for a logarithm looked like this. We said that y is equal to the logarithm base b of x because, well, if and only if, uh, that base b raised to the power y is equal to x. And if we think about the way this definition would be applied over here, it should make some sense. But I'll show you another version of this because there is a trick that we use, and we call it the exponentiation trick. All right, how does exponentiation work? So we're going to exponentiate, wonderful word, exponentiate both sides of your equation. How does that work? Well, in this case, we have a logarithm base 3. If we have a quantity a equals b, right, this is sort of the counterpart to our trick before. If a is equal to b, then it must be that our we could take our base here, or say u raised to that power a would equal to u raised to that power b. Right? So this is sort of the flip side to our trick from before, and that's what we're going to use here as well. So I have a logarithm. It has a base 3, the x plus 1, and that's equal to 2. Right? So I'm going to take advantage of a third rule here that says, well, look, I know that if I take base b and raise it to a logarithm base b of x, because the logarithm base b of x and b to the x are inverses of one another, they just undo each other. So I'm going to rewrite this and say, well, what if we take 3 and raise it to the logarithm base 3 of the quantity x plus 1? Well, then I would have to set that equal to 3 to the second power. And then we want to see if we can simplify both sides. Now, I chose this base 3 because that was the base of my logarithm, right? If it were some other base, I'd have to choose a different number. But what happens here is that, well, the logarithm and the base 3 exponentiation undoes each other and just leaves us with x plus 1 on the left-hand side. Now, on the right-hand side, we actually square 3, so we're going to get 9. And if we subtracted 1 from both sides, we would find that x equals 8 is the actual value of our solution. So, taking advantage of this exponentiation rule, we can actually use that sometimes to help us very quickly find the solution to a logarithmic equation of this simple kind, right, where we have a logarithm already isolated. But what if it's not isolated? Here's another example right here of this type. We have 3 minus the logarithm, natural logarithm this time, that's a base e, of x plus 2 is equal to 2. So what I'd want to do right here is before I start trying to use my rules, I'm going to try to isolate the logarithm, if I can. So I'm going to isolate the natural logarithm of x plus 2 before I do anything else in this equation. Well, to do that, that means that I'm going to have to gather some terms together. So maybe if I subtracted 3 from both sides of my equation, I might be able to come up with something. And if I subtract 3, I get the negative of the natural logarithm of the quantity x plus 2 is equal to negative 1. Well, for me, right, when I say a negative of something equals to the negative of something else, I can just divide both sides by negative 1 to determine that the natural logarithm of x plus 2 in this case is equal to positive 1. All right, so now we would try to exponentiate, right? So we're going to use that trick This time it says if A is equal to B, in this case, raising the base, what did we say in our last slide there? I want to keep isolated here. If I said the base U was raised to the power A, then it would be the same as the base U raised to the power B. In other words, I use the same base on both sides to exponentiate. So what base would be useful right here? Well, our base is already E, right? We could think of this as being the logarithm with a base E of that quantity x plus 2 is equal to 1. And we also know that essentially anytime we take a base A raised to a logarithm base A of x, the A base A and the logarithm base A undo each other and just give us x. So we're going to take advantage of this rule right here to help us out and exponentiate both sides with the base E. So we would have E raised to the natural logarithm of x plus 2 is E raised to the first power. And if we simplify, that gives us x plus 2 on the left-hand side of the equation. And e to the first is just itself. It's the number e. And so in exact form, we should write our solution as x equal to the quantity e minus 2. Now, again, we can approximate the answer if we wanted to get a calculator type of solution on this one. And since e is approximately 2.71828, we might be able to find a decimal solution like 0.71828 or so. But it doesn't really matter because this is the exact form of our answer. So we're going to leave our answer in this exact form in terms of e. The next thing we might do after this is, if we really needed it, we could use a calculator to get the decimal form, but we're just going to leave it in this form right here and we'll be done.